இந்த அட்டெண்டன்ஸ் எடுக்க சொன்ன
டெலிகிராம் கஷ்டமாடு இல்ல இதுவும் தருவாங்க
இதுல நம்பர்
சார் ரோட் ரெக்கார்டா
அவங்க நம்பர் ரெக்கார்டா
என்ன ரெக்கார்டா
அப்ப
Aduh, ibu nih registration number kan aku. Udah di ini. Jadi ya. Ya lebih. Udah kali naik mau. Ada ini. Ada itu ada. Jadi jangan itu lain.
Ini mute.
Harus kenal.
Okay, so we'll start. So welcome to the first Zoom lectures of this course. Basically, the plan of the faculty now is to conduct the lectures via Zoom until the government allows us to start the classes again. So we will be having our lectures via Zoom till further notice. So we will have our lectures according to our regular timetable on Zoom, right? So Monday 8 o'clock and Tuesday 1 o'clock and Saturday 9 o'clock is our regular class time for limit process. So we will have that class on those times via Zoom, and we will be sending the Zoom link for the classes on that day or a day before, right? Usually, and we will post this on our LMS as well as your Telegram group, which is run by the Dean's office. So basically, that is how the classes are going to be conducted as of now. And if once they decided to call you back, then only we can start thinking about giving you ICA exam. So right now we are postponing the ICA exam. So we will continue teaching, and once you come back to the classes again, we will decide a date for the exam, and then we will conduct the exam on that day. Right? So, but the material for test and the syllabus for the first test is not going to be changed. It is still the same, right? But the exam will be conducted when you come back to the university. So as I told you, because there is no exam today, we will start continuing chapter 2, and on Saturday class, as I told you earlier, you will be done a tutorial. So the tutorial, the teaching assistant will teach you about tutorial problems on the first chapter, as well as the leftover exercises which I left over in the first chapter, right? So that is the idea of the structure of lectures for today and Saturday. So today I will continue chapter 2, and Saturday you will have tutorial and leftover exercises which will be taught on Zoom by the teaching assistant. Right? So that is how the things are going on. Right? So right now we will go back to what we are learning. Right? So we have talked about a sequence, right? Xn, where Xn n belongs to natural number. We say that it is a sequence, right? And then we talk about limit n goes to infinity, Xn is equal to L, if and only if for every epsilon positive, there exists a natural number belongs to n, natural number n, such that the distance between Xn and L is less than epsilon for every n greater than n. Right? So this is what we learned last time, right? When we define sequence, right? So pi as limit of the sequence, right? So now, because you already know in A level how to compute the limit, right? So here what we are going to do is we are going to see examples where we prove that the certain limit exists by using this definition. Right? So here is the first problem. Right? I'm going to start as exercise. And so this you all know, 1 upon n, the exercise I did in the last class. Exercise show you that limit 1 upon n is 0, right? So we already draw the picture, right? Like the way we did here, right? So n and 1 upon n, and then you see that the sequence go like this and goes to 0, right? So we want to prove that, right? So if you want to prove this, then you have to show is for any epsilon positive, right? So you want for every epsilon positive, you have to show there exists n belongs to natural number such that 1 upon n minus 0 is less than epsilon for all n greater than n.
What's clear? Zoom பண்ணுங்க.
Okay, so you want to show that for every epsilon positive, like the definition, you want to show for every epsilon there exists n belongs to natural number such that 1 upon n minus 0 is less than epsilon. That is what you want to show, right? So you have to use the properties you learn already to show this result. Right, so like the way we do in Supremum, right? When we try to show the existence of square root of 2 in a previous example, we did some kind of a rough work and then we reversely do everything to get the results done. So here what we did is again, right? So you want 1 upon n minus 0 is less than epsilon. This is what you want, right? So this is equivalent to, you know that because n is natural number, so you can get 1 upon n is less than epsilon. Then if you show that, that is enough. So this is equivalent to, you know that 1 upon epsilon is less than n, right? So right, so technically you want to get So if you have taken an n such that n is larger than 1 upon epsilon, then you are done, right? So that is what you want to do. So for that, you already know the Archimedean property, right? So this is a rough work, right? So this is a rough work we did. So we know that, okay, we can get this results by Archimedean property. So if I get this, I can get here. So that is enough. I can start working out the proof. And so, okay, so I need to prove it for all epsilon. So let epsilon be a positive number, right? Then right, so clearly you know 1 upon epsilon is a real number, right? So right, by Archimedean property, we all know that there exists a natural number capital N, right, belongs to natural number such that 1 upon epsilon is less than n, right? So this you can write by using the Archimedean property. But what you want to show is for any small n greater than capital N, 1 upon n minus 0 is less than epsilon. That is what you want to show, right? So you can start working out, right? So right, so you all know for every small n greater than capital N, 1 upon n is smaller than 1 upon capital N, right? So that you all know. But because as long as capital N is smaller than small n, 1 upon small n is smaller than 1 upon capital. But 1 upon small n is equal to 1 upon n minus 0 absolute value. But by Archimedean property, you have here, right? From this, you know that 1 upon capital N is less than epsilon, right? Because of Archimedean property. So 1 upon n is less than epsilon. So here, because epsilon is arbitrary, you can prove it for all epsilon. Right? So that is now since epsilon greater than 0 is arbitrary, right? So you have for every epsilon positive, there exists n belongs to natural number such that 1 upon n minus 0 is less than epsilon for all n greater than n. So that is what you are trying to show. So this is the first example where you show that the limit of a given sequence is a certain value by using the definition. Right, so I'll leave a couple of minutes for you to write it down if you want to write it. And then we will move to the next exercise. So next exercise is this. Okay, so this is again something you learned in A level, right? So limit of this function is when you factor out n, you get 1 over 2 plus 1 upon n, and when n goes to infinity, that will goes to 1 half, right? So that you learn in A level. So again, you have to show it by using the definition, something like this, right? So you want this, right? So you want to show n over 2n plus 1 minus half is less than epsilon. This is what you want to show. So now I can see that this is equivalent to 2n minus 2n plus 1. So 1 over 2 times 2n plus 1, right, is less than epsilon. So clearly n is a positive number. So when you simplify, you get 1 over 2 times 2n plus 1, right? So that is obviously positive. So when you drop the absolute value, no change, still the same value. Right? But this says, right? So actually, this is enough, right? So because you know 1 upon 4n is smaller than 1 over 2n or 4n plus 2, right? So if this is less than epsilon, if 1 upon 4n is less than epsilon, then you can say that 1 upon 2 times 2n plus 1 is less than epsilon, right? So from here, you can go here, but it is not necessary that this implies this. So that is why I say from here to here, you can go. So, but this is basically equivalent to 1 upon 4 times epsilon is less than n. So this is Archimedean property. So the whole idea here is, right, whenever you want to show that something is a limit, right, so you basically want to show the sequence in term minus the limit absolute value of that is less than epsilon. Right? So you have to reduce that to some Archimedean property result, right? So your Archimedean property is some real number is smaller than natural number, or natural number is larger than a real number, right? So you have to, from this relationship, you have to reduce it back to some real number which depends on epsilon and a natural number which is larger than that. Right? So this is how you do this, right? So now once you get this, now you can write down the proof, right? So this is again a rough work. This is a rough work, right? So now we shall use this rough work and we will prove it according to the definition. Okay, so we will start as usual. We say let epsilon be positive, right? So then you know right, by Archimedean property, you know that there exists a natural number n such that 1 upon 4 times epsilon is less than that natural number n. Right? So for n greater than n, you want to show that n over 2n plus 1 minus 1 half, right? That is basically equal to absolute value of 1 over 2 times 2n plus 1. Right? So that is less than 1 upon 4n. But 1 upon 4n is less than 1 upon 4 capital N, because small n is larger than n. So 1 upon 4 times small n is less than 1 upon 4 times capital N. But 1 upon 4 times capital N is less than epsilon, because from here you know that 1 upon 4n is less than epsilon. So for every epsilon positive, there exists n belongs to natural number such that n over 2n plus 1 minus 1 half is less than epsilon 4 over n greater than. So that is the definition for the limit. So that is what we want to show. Okay, so next what we are going to do is we are going to show that the limit of a sequence, a certain sequence, does not exist. Right? So that is the next thing we are going to show. So one example we did last time is minus 1 to the power n. Right? So we see that minus 1 to the power n is oscillating between minus 1 and plus 1. So that is why we know that we don't have a limit for the sequence. Right? So here we are going to show that this limit of the sequence does not exist. So this exercise right? So we want to show limit of this sequence does not exist. Right. So if you want to show a limit of a sequence does not exist, right? So the easiest or more convenient way is to use the contradiction method. Right? So for a contradiction method, you know that you assume opposite of what you want to show, and then you get an obvious result which is against some concepts you already have, right? So that is how you do contradiction. So here I'm going to do the same thing, right? I'm going to assume, and I am going to assume that the limit of this sequence is L, right? So some fixed value L, and I am going to get a contradiction for that. So the idea is, you know that minus 1 to the power n will be minus when n is odd, and minus 1 to the power n will be plus 1 when n is even, right? So that is an obvious thing, you know, right? So first I will write the definition for this, right? Right? So for all n greater than n, absolute value of minus 1 to the power n minus 1 is less than epsilon. So minus L is less than epsilon, right? So we want to get a contradiction out of this. So what I am going to do is I'm going to choose because this result is true for all epsilon. Let me choose epsilon is equal to 1/2, right? So now what I am going to do is write n1 greater than n, right? Okay, so this is the definition I have for limit. Now I choose epsilon as a fixed value 1/2. So for that 1/2, I will have an n, right? N1 basically, and not n. So I will have n1, right? So there should be an n1 such that minus 1 to the power n minus L is less than half for all n greater than n1, right? Because we choose epsilon or we fix epsilon as half, right? So I rename the n as n. So you know that, right? So you know that 2n1 is obviously greater than capital N1. So if 2n1 is greater than capital N1, so this inequality is satisfied when small n is equal to 2 capital N1. Similarly, 2n1 plus 1 is also greater than capital N1. Right? So this inequality is again true for that value, which is 2n plus 1. So the reason why we choose is 2n is an even number and 2n plus 1 is an odd number. So for even power of minus 1 is plus 1 and odd power of minus 1 is plus 1. So this is equal to 1 minus L is less than half, and here it is absolute value of minus 1 minus L is less than, right? Right. So basically this is 1 minus L is less than half, and here minus 1 minus L. So I can factor out a minus 1 and take that minus 1 outside the absolute value. So that becomes plus. Right? So clearly this becomes 1 plus L is less than 1/2. So I want to get a contradiction from these two parts. So in order to get that, right, so you notice that 1 plus L plus 1 minus L, right? So you add these two parts, 1 minus L and 1 plus L. So if you add this, then you know this is actually equal to 2. Because 1 plus L plus 1 minus L, so that's 2. But you study triangle inequality in the first chapter, right? So let me break these two together. So now I apply triangle inequality. My triangle inequality says, right, when I add two numbers inside the absolute value, that is smaller or equal to adding the absolute value of those numbers separate. Right, so then 1 plus L and 1 minus L. Right, so this is less than 1 plus L is less than half and 1 minus L is less than half. Right? That is equal to 1. So here what you get is 2 is strictly less than 1. Right? And so what you have is 2 is strictly less than 1. That is obviously wrong, right? So you know that that is obviously wrong. 2 cannot be strictly less than 1. So this is a contradiction. So if this is a contradiction, then I know there is no limit. Right? So limit of minus 1 to the power n as n goes to infinity does not exist. Right. So far what we did is we use the definition to show that a certain real number is a limit of a sequence, and then again we use the definition to show that a certain sequence may not have a limit, right? So here minus 1 to the power n is one example. So we show that that does not have a limit, right? So now what we are going to do is we are going to see how many limits can a sequence have, right? So because we know that the sequence may have a limit or may not have a limit, right? So next question is, if a sequence has a limit, how many of the limits exist, right? Whether it is only one or whether there are many, right? So interestingly, the sequence, if it has a limit, then that should be the only limit, right? So the limit is unique for a sequence. So we shall prove that result by using the definition, right? So the uniqueness of the limit. So we can write that as a theorem. Right, so the sequence, if it has a limit, then it is unique, right? So we want to show that the sequence has a unique limit. So again, if you want to show that something is unique, you always assume that there are two limits and then you show that both of them are equal. So we are going to go the same way, right? Right, so let xn be the sequence and L1 and L2 be two limits of the sequence, right? So obviously you assume that so L1 is not equal to L2, right? So you know that right, so you know that if L1 and L2 are not equal, right? So clearly L1 and L2 are not equal. So absolute value of L1 minus L2 is greater than 0. So divided by 2 is greater than 0. So you choose epsilon as absolute value of L1 minus L2 divided by 2. So that is strictly greater than 0. Right. So now what we are going to do is we are going to write the definition for two limits, right? So because L1 and L2 are two limits, right? Right? Because L1 is the limit, right? So you can say that there exists capital N1 such that absolute value of xn minus L1 is less than epsilon, right? For all n greater than N1, but you choose epsilon as L1 minus L2 over 2. Right? Similarly, you write for the other limit. Okay, so now because L2 is also a limit, you can write the same definition for L2. Right, so xn minus L2 is less than absolute value of L1 minus L2 over 2. Right. So now you have two definitions for limit. Now what we are going to do is we are going to combine them. Right. So in order to combine them, you know that this result is true for n greater than capital N1. This result is true for n greater than capital N2. So if you choose the largest of those two, N1 and N2, then obviously these two results hold for both of them. Right? So what we do is we choose okay, so we choose capital N as the maximum among the two numbers N1 and N2. Right? So then obviously if small n is greater than n, then clearly small n is greater than n1 and small n is greater than n2, right? Right, so if n greater than n1, then clearly n greater than n1 as well as n greater than n2. So now we can combine the two definitions of limit. Okay, so clearly for all n greater than n, both xn minus L is also less than half of L1 minus L2. At the same time, xn minus L2 is also less than half of n minus L1 minus L2. Right. So in that case, but you know that L1 minus L2, you can write it as L1 minus x capital N plus 1 and then plus x capital N plus 1 minus L2, right? Because this cancel this, so there is no difference. Right. So now what you do is you apply triangle inequality. Right. Triangle inequality. This is L1 minus xn plus 1 and a plus xn plus 1 minus L2. Right. So this is less than half of L1 plus L2. The other one is also less than half of L1 plus L2. So this is less than half of L1 minus L2. This is also less than half of L1 minus L2. So if you add that, that is L1 minus. So what you have is absolute value of L1 minus L2 is strictly less than absolute value of L1 minus L2. That is not possible, right? So same number cannot be strictly less than, right? So here strictly less than. So same number cannot be strictly less than the same number itself. And so that is a contradiction. So this is a contradiction. So the only possibility is L1 and L2 are same. So that proves that the sequence of a limit of a sequence, if it exists, it is unique. Right? All right. So So far what we did is, we define what do we mean by a limit of a sequence, and then we use the definition to show that a certain real value is the limit of that sequence, and then we use the same definition to show that certain sequences will not have limit, and then we prove that if limit of a sequence exists, then it must be unique, right? So there will be exactly one limit for a sequence. And again, from your A-level knowledge, you must have seen some limits where the limit is infinite, right? So as long as x grows or n grows, the function grows to infinity, right? So you have seen such kind of function. Let's say, for example, right? So if I have a sequence n, right? So if my sequence xn is n, right? So you can see that the natural numbers, this is my xn. So when n is equal to 1, this is 1. When this is 2, this is 2. This is 3, this is 3. This is 4, this is 4. Right? So you can see that my sequence grow and grow all the way to infinity, right? As long as n increases, my sequence goes to infinity. Similarly, if I have my sequence xn as minus n squared, right? Minus n squared. At 1, I will have 1. At minus, sorry, at 1, I will have minus 1, right? At 2, I will have minus 4. At 3, I will have minus 9. So my sequence will go like this to minus infinity, right? Minus n squared is a sequence that will goes to minus infinity, and plus n is a sequence that will goes to plus infinity as n goes to infinity. Right? So those two are possibilities. The sequence which goes to negative infinity and the sequence which goes to positive infinity. So that means a sequence with an infinite limit, positive infinite limit, and a sequence with a negative infinite limit. So let us define the positive infinite limit and negative infinite limit now. Right, so we say that xn tends to positive infinity as n tends to infinity, right? As n tends to infinity, xn tends to positive infinity if there exists n such that, right, for every k greater than 0, xn is greater than 0, right? So after some point capital N, right, so this, there is a k, right, and this function value or the sequence value is greater than that function value for all n greater than n, right? So if you show that, then we say that the limit of the sequence is positive infinity, right? Similarly, you can say for minus infinity as well, right? So let me use it as a notation, right? So we say xn tends to minus infinity as n tends to infinity, right? If for every k negative, there exists n belongs to natural numbers at that xn is less than k for all n greater than n. Right? So negative infinity tends to negative infinity. Instead of writing tends to, I can put an arrow, right? So again, n tends to infinity. So instead of putting arrow, instead of writing tends to, I put arrow. Right? So that is a common notation again to denote tends to, right? So that means it's going to. So for every k negative, there exists a natural number such that xn is less than k for all n greater than n. So this is how we write the definition for the infinite limit, right? So sequence which goes to infinity. In the next class, again Saturday 9 o'clock class, you will have tutorial discussion and worked example discussion from chapter 1. And next Monday class, if it is continuing on Zoom, then we will continue from this definition of infinite limit, right? So that we will see in the next class.